Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is batteries. Our objective today is to perform a brief introduction to the battery, an electrochemical energy storage device. We'll introduce common terms and concepts used to describe batteries and differentiate between different types of batteries. This lecture operates under the presumption that you are at least marginally skilled in basic DC circuit analysis. If you need to brush up on this skill set, by all means check out the Basic Electronics 1 DC Circuit Analysis playlist available at the Big Bad Tech channel. A brief disclaimer before we begin. Always consult the manufacturer's datasheet for a particular battery of interest. Do not assume for a moment the specifications presented herein are universal in nature. Batteries can explode into a ball of white-hot fire or otherwise be damaged and rendered useless if you charge or discharge them incorrectly. A battery is an energy storage device, and as such represents stored hazardous energy if it is not properly locked out and tagged out. A short circuit across the terminals of a battery, be it from a conductive tool or an errant wire that bridges the terminals, can produce a high current and damage the battery. Take necessary precautions when working around or with batteries. Let us begin. A battery is an electrochemical energy storage device. During the charging process, a battery is supplied DC electrical energy, which changes the balance of charge between the chemically active materials central to the internal electrochemical reaction. The charge process converts DC electrical energy into stored chemical energy. A battery can also be viewed as a portable source of electrochemical energy. During the discharge process, a battery converts the stored chemical energy into DC electrical energy via the reversed electrochemical reaction. The discharge process will continue until the active material in the battery is exhausted and can no longer support charge flow. The discharge process converts stored chemical energy into actively used DC electrical energy. The DC nature of the battery means that power electronics intermediaries must be used to charge and discharge the battery using AC sources or AC loads. An AC source must first be rectified to DC with the appropriate magnitude and polarity if it is to charge a battery. A power electronics device, known as an inverter, must invert the stored DC energy in the battery into an AC waveform with the appropriate magnitude, frequency, and phase shift in sequence if it is to drive an AC load. This is to suggest that the rectification, charge and discharge, and inversion process, being part of a multi-stage chain of conversion, extract losses due to inefficiencies. Batteries, as most of us know them, are finicky. They are expensive, have a limited lifespan, are heavy, bulky, require maintenance, are slow to charge, and only have a limited capacity. However, with rapid development within the battery field, there exists the possibility of a disruptive battery technology with long life, high specific energy, high energy density, high power output on demand, one that requires minimal maintenance, safely operates in a wide range of temperatures, and all available at a reasonable cost. This is when things will get interesting. We'll come back to discuss some of the $10 words I used in a moment. Applications for batteries beyond that of powering portable electronics are limitless. Intermittent energy sources like the sun and wind only produce energy during daylight or windy conditions. Solar arrays and wind turbine generators, in combination with battery storage, can ensure continual and reliable energy access during periods of low illumination or no wind. On a small scale, off-grid residences in ordinarily remote and inhospitable locations can remain comfortable and well lit. On a large scale, grid-level energy storage of renewable resources can be used to manage the grid. Renewable energy can be stored during periods of surplus production. During periods of excess demand, the energy can be withdrawn. Uninterruptible power supplies, or UPSs, keep critical information handling or industrial tasks from crashing during an unexpected loss of power. Batteries can replace the gas tank in a passenger vehicle. Instead of gas or diesel being used to power a traditional internal combustion engine, electricity can power a motor, all without the associated thermal inefficiencies, noise, emissions, and the geopolitical consequences of ensuring a constant supply of petroleum. As rosy a picture I'm painting of this transformative technology, be wary of sensational claims of the next big thing in batteries. To be certain, there are promising developments in the experimental stages grounded in solid science. But there also exists a disproportionate number of claims based in hype, speculation, wishful thinking, and sheer nonsense. During the course of this lecture, I will entirely neglect or only mention in passing some new battery developments and largely restrict our analysis to those batteries presently and commonly available. The first distinction between different types of batteries regard their relationship with the charge and discharge cycles. A primary battery is meant to be discarded when discharged because they are not economically rechargeable. A common example of primary batteries are alkaline manganese or alkaline batteries for short. A secondary battery, in contrast, is a rechargeable battery and can undergo a finite number of charge and discharge cycles. This lecture primarily discusses secondary batteries. Sometimes individuals identify a third type of battery in the form of a reserve battery, meaning a battery intended for long-term storage with an inherently low self-discharge rate. Reserve batteries sometimes physically isolate or render chemically inert the active materials central to the electrochemical reaction until such time they are needed for use. Secondary batteries can also be differentiated by their internal chemical makeup. One might ordinarily encounter lithium polymer, lithium-ion, which could be either lithium iron phosphate, lithium cobalt, or lithium manganese, lead-acid batteries, and nickel metal hydride. Nickel metal hydride has become a common consumer-level rechargeable battery that has largely replaced nickel-cadmium batteries due to toxicity and environmental concerns, as well as resolving the memory effect of NiCad, which is the progressive loss of capacity for batteries not regularly exercised throughout their range. Each chemical constitution brings with it certain advantages and disadvantages in terms of complexity, safety, operating range, durability, size, weight, and of course, cost. We'll discuss these observed differences in a moment. The functional unit that makes up a battery is an individual cell. A lead-acid cell has a nominal cell voltage of approximately 2.1-ish volts. A lithium iron phosphate cell has approximately 3.2 volt nominal cell voltage. A lithium polymer cell, depending upon construction, can have a cell voltage of approximately 3.7 volts. We'll discuss the significance of nominal values in a moment. One assembles a battery by placing collections of these cells in a series aiding configuration, where the subsequent cell's negative terminal is attached to the previous cell's positive terminal. 3 lead-acid cells in a series aiding configuration make an approximately 6-volt lead-acid battery. 6 lead-acid cells in a series aiding configuration make an approximately 12-volt lead-acid battery. 3 lithium polymer cells in a series aiding configuration would make an 11.1-volt battery. This is the logic behind the schematic symbol used for a DC power source. It represents a stack of series aiding cells forming an increasingly large voltage differential between the original negative terminal and the last positive terminal. Each cell has 2 electrodes submerged in an electrolyte, sometimes with a porous separator between. The electrolyte is basically an electrically conductive fluid. The electrolyte can be liquid, an amorphous gel, or absorbed in a fiberglass mat. A flooded or wet battery makes use of a liquid electrolyte. An example would be the battery in your car. The electrolyte is an aqueous mixture of water and sulfuric acid. While inexpensive, flooded lead-acid batteries, sometimes called FLA batteries, are confined to those applications in which the orientation of the battery is invariably upwards. Ideally, your car is always upright, and flooded batteries, quite like a bottle of acid without a top, cannot be expected to work on their side or upside down. Given a flooded battery is quite literally an open container, one must not only keep it upright, one must also expect to regularly maintain the electrolyte at a certain minimum level. As we'll later learn, the charge process produces gases from the electrolyte, which if unregulated, can quite literally boil it away. Valve-regulated, sealed, or maintenance-free, notice the quotation marks, overcome these limitations by using an electrolyte that will not spill out if the battery is placed in an other than upright orientation. The two most common forms of valve-regulated lead acid, sometimes called VRLA or SLA for sealed lead acid, are gel cells and absorbed glass mat, or AGM cells. The electrolyte in a gel cell is a viscous gel, and AGM batteries feature a fiberglass mat between the electrodes that contains the electrolyte. The dry nature of the electrolyte means VRLA batteries can be used or stored in any orientation. The gases inside VRLA batteries are retained and are catalytically recombined. The valve's only function is to vent the battery in the event of internal pressure exceeding a safe value, and a gas's loss to venting cannot be easily replaced. For this reason, the electrolyte in VRLA batteries is often over-provisioned. The reduced maintenance requirements and the ability to use or store a VRLA in any position comes at a price of reduced mobility of the electrolyte, and in contrast to a flooded cell, the chemical reactions ordinarily proceed at an impeded rate. A quick note about the terminology I'm using in this generic cell diagram. The positive electrode is the cathode. The negative electrode is the anode. Those with an understanding of basic power electronics devices like the diode might think I'm playing a little fast and loose with the definition of cathode and anode. A forward bias diode has its anode at a higher or more positive voltage with respect to its cathode. The definitions for cathode and anode have actually nothing to do with polarity, but rather are functional in nature. A cathode is defined as the point where conventional current leaves. Conventional current leaves the cathode of a battery when the battery is supplying conventional current, just as conventional current leaves the cathode of a diode when the diode is forward biased. An anode is defined as the point where conventional current enters. Conventional current enters the anode of a battery in the return loop of the circuit when the battery is supplying conventional current, just as conventional current enters the anode of a diode when the diode is forward biased. These definitions only extend to the functionality of the electrodes external to the battery during discharge, because, as we'll see in a moment, there is a charge movement internal to the battery, and the direction of current is reversed during the charge process. I don't wish this lecture to devolve into a chemistry lesson. I do, however, wish to discuss the general reactions that occur inside a typical battery, at least in very basic terms, because it's essential to your understanding of the observed electrical properties during charge and discharge. I'm going to use a lead-acid battery as an example, with the understanding that other chemistries necessitate different players. For those well-versed in chemistry, you will note that I am playing fast and loose with the reaction, neglecting stoichiometric balancing, and summarizing it to a very simple process. If your goal is an understanding of the electrical aspects of a battery, the nitnoid chemical details can be summarized as such. At its most basic level, a charged battery is one in which there is a chemical imbalance. A charged lead-acid battery has a lead peroxide cathode and a spongy lead anode. There is a chemical difference between the cathode and anode. These electrodes are immersed in an electrolyte. In the case of a flooded lead-acid battery, a mixture of sulfuric acid and water with a given concentration. The aqueous solution of sulfuric acid and water disassociates some of the hydrogen ions from the sulfuric acid molecule, forming positively charged hydrogen cations and negatively charged HSO4 anions. The concentration of the acid-water electrolyte mixture is a direct means of ascertaining a given battery's state of charge, although not exactly the most convenient means of doing so. We'll discuss specific gravity measurements using a hydrometer and alternate means of measuring state of charge in a moment. Before we delve deeper into this analysis, I must remind you that conventional current flows from the positive terminal of an active source to the negative terminal. However, electrons, the negatively charged particles that actually constitute current flow, really move from the negative terminal to the positive terminal. If an ammeter measures a quantity of positive 2 amperes moving through the electrical load, in actuality, it means 2 coulombs per second of electrons are moving in the opposite direction. During the discharge process, an electrical load links the cathode to the anode via a closed electrical circuit, and a transfer of charged particles from the cathode to anode and vice versa via both the closed electrical circuit and the electrolyte can begin. At the anode, the spongy lead combines with the HSO4 anion, forming lead sulfate, and some spare electrons are free to move through the closed electrical circuit. The electrons, by moving from the negative terminal to the positive terminal, mean an equal amount of conventional current is traveling from the positive terminal to the negative terminal. Again, conventional current is the opposite of electron flow. At the cathode, lead peroxide combines with the HSO4 anion, the incoming electrons from the closed circuit, and hydrogen cations to also form lead sulfate and water. Again, do not stress out about the stoichiometric balancing at the individual electrodes. The whole reaction summates to lead peroxide at the cathode, plus spongy lead at the anode, plus the ions from the dissociated electrolyte, yield lead sulfate at both the cathode and anode, a quantity of water, and energy in the form of electrons moving from anode to cathode via our closed electrical circuit. This is the take-home point. During the process of discharging the battery, not only has the cathode become progressively less lead peroxide and more lead sulfate, the anode has also become less spongy lead and more lead sulfate. The previous chemical differential between the electrodes has been slightly eroded, and they have become more chemically alike in the process. Not only has this chemical differential between the electrodes been slightly reduced, also consider the concentration of the electrolyte. Sulfuric acid has been consumed by both electrodes, and in its place, water has been substituted. It is for this reason that a specific gravity reading of the electrolyte, measured using a hydrometer, is a direct means of ascertaining a battery's state of charge. Specific gravity is a dimensionless ratio of the density of a fluid, in this case the electrolyte, compared with that of water. Water with a density of 1 gram per cubic centimeter, when compared to water, also at 1 gram per cubic centimeter, will have a specific gravity reading of 1. Something denser than water, like an aqueous mixture of water and sulfuric acid, will have a specific gravity reading higher than 1. A fully charged battery will have a greater concentration of acid in the electrolyte and exhibit a specific gravity higher than that of water. A fully charged, flooded lead-acid battery will ordinarily have a specific gravity reading of about 1.265, meaning it is more acidic and less water-like. This specific gravity reading roughly translates into a charged flooded lead-acid battery as having an electrolyte concentration of 35% sulfuric acid and 65% water. A deeply discharged battery, in contrast, will have less acid in the electrolyte and exhibit a specific gravity closer to that of water. A deeply discharged flooded lead-acid battery might have a specific gravity reading of 1.120, meaning it is less acidic and more water-like. This specific gravity reading roughly translates into a discharged flooded lead-acid battery as having an electrolyte concentration of 15% sulfuric acid and 85% water. A hydrometer, used to obtain specific gravity readings, is a means of directly measuring electrolyte acid concentration. Given density is subject to temperature, a hydrometer should be temperature compensated to obtain accurate specific gravity readings. Here's a discharged 3-cell flooded lead-acid battery. The hydrometer used to measure one of the 3 cells shows a specific gravity of about 1.150. The hydrometer is again measuring the concentration of acid internal to the cell, and an individual making use of a hydrometer must take necessary precautions to prevent a spill or splash. Wear the proper PPE and move purposely and cautiously when taking a hydrometer reading. This cell has a low specific gravity reading, meaning the electrolyte is more water and less acid. The other cells show similar readings. If there was a marked differential between one of the cells, one might suspect the inordinately low cell is being damaged. Given a battery is a series arrangement of cells, one can use basic series properties to determine the effect of a damaged cell. Voltage is additive in a series aiding arrangement, and current through elements in series is the same. A damaged cell with no voltage across it will reduce the battery's voltage by that amount. A damaged cell not permitting current through it will effectively cut off current produced by the whole battery. In this case, though, all 3 cells read close to the same low value, and we can rest assured that this battery is uniformly discharged. The hydrometer readings, although an accurate means of directly ascertaining battery state of charge, are not exactly the safest and most convenient means of doing so. Not to mention that taking direct readings of the electrolyte concentration would be impossible for sealed batteries. It is for this reason that most individuals ordinarily resort to testing the open circuit voltage of a battery with a DMM and DC voltmeter mode as a means of indirectly ascertaining state of charge. Though not a direct means, the DMM is a substantially more convenient means of doing so, with significantly less chance of getting acid flicked into your eyes or dumped on your pants. A DMM reading the open circuit voltage of this discharged 3-cell battery reads close to 5.95 volts. One might think this is close enough to the nominal value of 6 volts. However, as demonstrated by the direct reading of the electrolyte concentration by the hydrometer, this is somewhat misleading. Nominal values, as the name implies, are in name only and are assigned as convenient designations. As is true in many aspects of life, operating conditions may vary. A nominal 12-volt battery might have a working voltage of 14.4 volts during one stage of the charging process, an open circuit voltage of 12.8 when fully charged, an open circuit voltage of 11.8 volts when deeply discharged, and might even drop to a working voltage of 10.8 volts when delivering a brief but intense burst of current, as in when a starter battery is used to start a car. This is to suggest that the nominal 12-volt value is merely a point on the operating curve of this battery and a single picture of a moving target. With the understanding of this operational range, one can approximate the magnitude of the open circuit voltage, i.e. when the battery is not connected to a load, across the terminals of a battery as a roughly linear measurement of that battery's state of charge, where state of charge, or SOC, is expressed as a percentage of the remaining energy capacity. State of charge is also sometimes called residual capacity. We'll discuss the specifics about battery energy capacity measurements in a moment. The state of charge is essentially a quick estimate of how much gas is left in the tank. A nominal 12-volt battery that has an open circuit voltage of 12.6 volts is about 80% full, whereas one that has an open circuit voltage of 12 volts is only about 10% full. Again, this linearity is an approximation only, and at extremes of the range, the linearity fails to hold true. This being said, it's good enough for our purposes, and a lot less messy and substantially more convenient than taking hydrometer readings of the electrolyte. If we scale this same curve to a nominal 6-volt battery, we realize our previous open circuit voltage reading of 5.95 volts is actually an indicator that this battery is in pretty rough shape and essentially running on empty. Flooded lead-acid batteries are a type of secondary battery and can be recharged. Charging a battery is essentially the reverse of discharge. During the charge process, conventional current is forced into our previously labeled cathode, or using electron flow theory, electrons are forced into the previously labeled anode. The functional definition of the cathode and anode have changed during the charge process, but to avoid confusion, let's keep them the same. Again, neglecting stoichiometric checks and balances that so entertains the chemists of the world, what essentially occurs is that the sulfate is forced out of the spongy lead anode at the same time the sulfate is forced out of the lead peroxide cathode. The anode and cathode, via the charging process, become chemically dissimilar, and the chemical imbalance is restored. Additionally, the electrolyte becomes more acidic in nature and less water-like. The chemical reaction is essentially the reverse of discharge. By being provided electrical energy from an external source, the battery is compelled to store electrical energy in a chemical imbalance. In a perfect world, a battery would be a limitless vessel for repeated charge and discharge cycles. However, a full discharge causes strain, and each cycle permanently robs the battery of a small amount of capacity. Lead-acid batteries that are regularly deeply discharged and then undergo long periods without a charge experience something known as sulfation, in which the lead sulfate crystals harden and become increasingly difficult to remove during the charge process. As more and more effective area is removed from use, not only is capacity reduced, the chemical reaction proceeds at a reduced pace. This is the principal difference between a starter and a deep cycle battery. A starter or SLI battery for starting, lighting, and ignition is designed to produce a substantial amount of current for a brief moment, and then immediately be recharged by the car's alternator when the engine is running off diesel or gas. SLI batteries aren't designed to be deeply discharged. However, they can supply a large quantity of power for a very brief moment of time. An SLI battery is designed to win a sprint. A deep cycle battery, in contrast, is one that is designed to run various loads for long durations and may not see consistent or regular charging. A deep cycle battery is designed to win a marathon. Additionally, deep cycle batteries used to supply an off-grid application may experience irregular charging and must be flexible in nature. Intermittent renewable resources might charge a battery slowly, yet a backup generator will charge a battery quickly. Additionally, consider UPS applications in which a battery is on constant standby and only expected to back up a load for a brief grid disturbance or initiate an orderly shutdown of the affected system. This is to suggest that no one battery design does it all. At the two extremes are starter and deep cycle batteries. A starter is a sprinter and designed to deliver a large surge of power for a short duration. A deep cycle battery is a marathon runner and designed to be a lasting source of energy. Energy is different than power. Power is the time rate expenditure or production of energy. Power is energy over time. For those still struggling with this concept, I am emphatically recommending you take the time to visit the Energy and Power lecture available at the Big Bad Tech channel and correct any misconceptions you may have on this topic. Energy can be visualized as a quantity of gasoline in a tank. If you wish to travel a great distance, you need a tank full of gas, and you need to use it efficiently. Power, in contrast, is the time rate withdrawal of gas from the tank. If you go up a hill at a great speed, you'll consume more gas per second and empty your tank quicker than if you traveled at a reasonable speed on a flat road. Energy is measured in units of foot-pounds force, or joules, where 1 joule is a newton of force expressed for a distance of 1 meter. Power, in contrast, is measured in units of foot-pounds force per seconds, or watts, where 1 watt is 1 joule per second. Power is a unit of energy, the joule, per unit of time, the second. Power is energy over time. SLI batteries are designed to deliver their energy content in a short but intense high-power burst. As such, the physical construction of the SLI battery is designed to maximize current flow by maximizing surface area. Starter batteries are composed of a large quantity of thin electrode plates. The emphasis is on power delivery rather than energy capacity. A deep cycle battery, in contrast, is designed for energy capacity and a high cycle count. A deep cycle battery is composed of a smaller number of thicker and more robust electrode plates. The energy capacity of a battery is ordinarily expressed in units of amp hours, which, if you followed our previous discussion of power and energy, should frustrate you to no end. Energy is ordinarily measured in units of joules. However, a brief explanation of the amp-hour unit should be sufficient to clarify this choice of units, although to do so necessitates a brief diversion. First, let us turn our attention to the unit of watt-hour. The watt-hour is not a unit of power. The watt-hour is a unit of energy. I know there's a watt in there, but look at it. It is a unit of power, the watt, times a unit of time, the hour. If power is energy over time, it stands to conjecture that energy is power times time. The only thing necessary to find an equivalency between the watt-hour and the joule is a unit conversion. If 1 watt is 1 joule per second, and 1 hour is 60 minutes, and 1 minute is 60 seconds, the chain of unit conversion yields 1 watt-hour equals 3,600 joules, or 3.6 kilojoules. This is why people use the watt-hour in preference of the joule. Joules are tiny, annoying units. Consider the kilowatt-hour. The kilowatt-hour is the common unit of energy for residential electrical customers. A kilowatt-hour represents 1,000 joules per second being used for 1 hour. The chain of unit conversions yields 1 kilowatt-hour equals 3,600,000 joules, or 3.6 megajoules. Again, the joule is a tiny unwieldy unit, and it is for this reason energy usage is normally expressed in units of watt-hours, kilowatt-hours, or even megawatt-hours or gigawatt-hours for large-scale energy generation and usage calculations, where each next higher engineering prefix represents a magnitude 1,000 times higher than the one below it. Returning to our discussion of the amp hour, electrical power is the product of voltage and current. P equals V times I. Units of watts equals units of volts times units of amps. The energy unit amp hour assumes a user is comparing batteries with comparable voltages. What is missing when expressing the energy capacity of a battery in amp hours is the nominal voltage of the battery. Energy is power times time. Power is voltage times current. Energy is voltage times current times time. Amp hours is only 2/3 of the picture. Like I've said previously, if being an electrical engineering technician was easy, everyone would be an electrical engineering technician. By being unnecessarily coy with energy units, battery manufacturers ensure that no one off the street can figure out what they're talking about, and electrical engineering technicians can still make top dollar interpreting such unnecessary obfuscations. Capacity is largely determined by the type and amount of active material. All other considerations being equal, physically larger batteries have larger capacity. Here are 3 batteries with the following capacities: 7 amp hours, 24 amp hours, and 230 amp hours. Realize, however, we're not exactly comparing apples to apples, because the 2 valve-regulated lead-acid batteries are 12-volt batteries, and the FLA battery in the back is a 6-volt battery. This means in a perfect world, the small battery has 12 volts times 7 amp hours, or 84 watt-hours, or 302.4 kilojoules. The middle battery has 12 volts times 24 amp hours, or 288 watt-hours, or 1.0368 megajoules, and the large battery in the back has 6 volts times 230 amp hours, or 1,380 watt-hours, 1.38 kilowatt-hours, or 4.968 megajoules of energy. Though, as we'll soon learn, capacity, quite like nominal voltage, is a moving target, and this single figure is a snapshot of a curve. The same observations can be made about primary alkaline batteries. A AAA battery typically has a capacity of around 1,150 milliamp hours. A AA battery typically has slightly more than double this capacity at around 2,870 milliamp hours. A C-cell battery typically has an energy capacity of approximately 7.8 amp hours. A D-cell battery typically has a capacity of approximately 17 amp hours. In this case, we're comparing apples to apples, because despite their size and capacity differences, these primary batteries have identical chemistries and identical voltages. All these batteries have a nominal voltage of 1.5 volts. Do not be fooled into thinking that a 1.5 volt C-cell battery with a 7.8 amp hour capacity has more energy than a 12 volt VRLA battery with a 7 amp hour capacity. It doesn't. Again, amp hour rating is only 2/3 of the picture. In a perfect world, a 12 volt VRLA battery with a 7 amp hour capacity has 84 watt hours, or 302.4 kilojoules of energy, whereas the 1.5 volt C-cell battery with a 7.8 amp hour capacity actually only contains 11.7 watt hours, or 42.12 kilojoules of energy. In a perfect world, a 12 volt battery with a 24 amp hour capacity would be able to provide 24 amps for 1 hour, 12 amps for 2 hours, 8 amps for 3 hours, 6 amps for 4 hours, 4 amps for 6 hours, 3 amps for 8 hours, 2 amps for 12 hours, 1 amp for 24 hours, or any other combination of amperages and hours that equals 24 amp hours. the whole time maintaining a flatline 12 volts. This isn't really the case, because as we'll later learn, not only does the rate of discharge affect the capacity, the voltage output noticeably dips as a battery reaches the end of its capacity. These observed effects should come as no surprise. Those that have trained for an athletic event are no doubt aware that a weekly regimen of hour-long training sessions have nowhere near the intensity of a 5-minute fight. It would be expected that a 24 amp-hour battery being asked to supply 24 amps at a dead sprint wouldn't last the full hour. Additionally, as the battery reaches the limits of its capacity, the electrochemical reactions central to the process could be expected to slow down as active material and functional surface area are consumed. To further complicate matters, with increased current draw, the output voltage is reduced because of a voltage drop across the internal resistance of the battery. We'll discuss the dirty details of discharge characteristics in later lectures. Let's move on to discuss different battery characteristics, notably the C rating, specific energy, energy density, specific power, depth of discharge, and lifespan. The C rating of a battery is undoubtedly the slipperiest of specifications, and misrepresentation and misinterpretation of capacity can occur if used improperly. The C rating of a battery is a means of relating energy capacity to the rate of discharge. As previously discussed, the real observable energy capacity of a battery is dependent upon rate of discharge, and a battery cannot be expected to deliver the same amount at a dead sprint when the electrical load is chugging current in great quantities in comparison to a leisurely stroll when current is casually sipped by the load. It is for this reason most batteries' nominal capacity in units of amp hours is expressed at the same rate, placing every battery on the same playing field, though as we'll learn, this isn't always the case. A C20 rating is the capacity of the battery in amp hours as if it delivered a constant current for a period of 20 hours. A battery with a C20 capacity rating of 7 amp hours means this battery delivered not 7 amps, but rather 350 milliamps every hour for a period of 20 hours until the electrochemical reaction central to the conversion process is exhausted and the battery reaches a predetermined cutoff voltage. Again, we'll discuss the dirty details of battery discharge characteristics in later lectures. However, any further discharge beyond the predetermined cutoff voltage may permanently damage the battery. The C rating, in effect, establishes a predetermined length of time and a firm cutoff to level the playing field. The misinterpretation of C rating values comes from two sources. First, one must inspect the datasheet of a particular battery to determine which C rating the nominal energy capacity is meant to represent. Again, the nominal capacity of a battery is a snapshot for a particular discharge period, or C rating. Ordinarily, most nominal battery capacities are rated at the C20 rating. However, batteries central to off-grid storage are often rated at the C100 rating, meaning the nominal capacity is determined over a longer period of 100 hours. Current draw for the lengthier C100 rating is proportionately lower than a more rapid discharge like the C20 rating. Do you see the chicanery that could result from misrepresentation of capacity? A 7 amp hour battery at the C20 rating delivers 350 milliamperes for a period of 20 hours, whereas a 7 amp hour battery with a C100 rating gets to kick back and only dispense 70 milliamperes for a period of 100 hours. These two ratings are not equivalent. It would be no surprise that the battery with a 7 amp hour C100 rating actually outputs less energy if you kick the chair out from under it and held it to the same rigorous C20 test. This is to suggest that you must be aware of what standards the battery will be held to for a particular application. A UPS might only briefly require energy to ride out a momentary grid disturbance or initiate an orderly shutdown of an affected system, whereas a battery for a mission-critical off-grid application may have to ride out several days of no sun or wind before the next recharge. A battery with a nominal energy capacity expressed in terms of the C100 rating gives a false picture of that same battery's capacity when withdrawn more rapidly over the course of 20 hours. Second, a misinterpretation of C ratings stem from the fact that discharge current rates and the maximum safe discharge rates are often expressed as a function of rated capacity. A battery with a C20 rated nominal capacity can be discharged at the 0.02 C20 rate, the 0.05 C20 rate, the 0.1 C20 rate, the 0.2 C20 rate, the 0.5 C20 rate, the 1 C20 rate, the 2 C20 rate, or any other combination. For example, a battery with a nominal 7 amp-hour capacity determined using the C20 rating would be discharged at the following rates. 0.02 C20 would be 140 milliamperes. 0.05 C20 would be 350 milliamperes. 0.1 C20 would be 700 milliamperes. 0.2 C20 would be 1.4 amps. 0.5 C20 would be 3.5 amps. 1 C20 would be 7 amps, and 2 C20 would be a whopping 14 amps. Key to your correct interpretation of the C ratings are these two figures right here, 0.05 C20 and 1 C20. A battery with a nominal 7 amp-hour capacity at the C20 rating will not output 7 amps for 1 full hour because the nominal 7 amp-hour capacity has been expressed at the C20 rating or for a period of 20 hours. It should not come as a surprise that the battery would last less than 1 hour if you were drawing 7 amps from it. Additionally, it should be self-evident that a battery with a 7 amp-hour capacity at the C20 rating cannot produce 7 amps for 20 hours. Otherwise, it would have a 140 amp-hour rating. That's not what the nominal capacity at C20 rating means. The only way you're going to get 7 amp hours out of this battery is when you discharge it over a period of 20 hours. This means the 0.05 C20 rate, where 0.05 is 1 over 20, will deliver 7 amp hours. 350 milliamperes times 20 hours equals the C20 nominal rating of 7 amp hours. Dig? Any electrical load drawing more than 350 milliamperes will deplete the battery faster and deliver less than 7 amp hours of energy. Any electrical load drawing less than 350 milliamperes might see the battery last longer than 20 hours and deliver slightly more than 7 amp hours of energy. It makes sense. You'll last longer when you perform a leisurely stroll than you do at a dead sprint. Regarding maximum safe discharge rates, C ratings are often used to express how much current a battery can safely produce. This is another major source of confusion regarding C ratings. In this sense, the C rating is again a function of the nominal capacity. For example, a 7 amp hour nominal capacity battery that can be safely discharged at 4 times the C rating can safely deliver 28 amps, whereas one that can deliver 8 times the C rating can safely deliver 56 amps. Again, with your understanding of the inverse relationship of battery demand and supply, one could be reasonably certain that batteries, regardless of the magnitude of the safe discharge, will deplete themselves significantly faster and deliver significantly less energy than the nominal 7 amp hours when discharged at such high rates. In this case, the C rating is meant to be an expression of a battery's maximum safe discharge current. It should be self-evident that this does not mean the battery can supply 28 amps for 20 hours, 28 amps for an hour, 56 amps for 20 hours, or 56 amps for 1 hour, or any other combination of nonsense. Again, we'll return to discuss the dirty details of battery discharge characteristics in later lectures. The C ratings might take some repeated exposure, so don't think this will be the last time you hear about them. Specific energy and energy density are two battery specifications that respectively express energy content as compared to battery mass and battery volume. Specific energy is the ratio of battery energy content in units of watt-hours over the mass of the battery in kilograms. Batteries with higher specific energy values deliver the same amount of energy and weigh less than a battery with lower specific energy. Energy density is the ratio of battery energy in contents of units of watt-hours over the volume of the battery in liters. Batteries with higher energy density values deliver the same amount of energy yet are smaller than a battery with lower energy density. Compare and contrast the differences in specific energy and energy density values of various battery chemistries. A lithium polymer cell might exhibit a specific energy of approximately 180 watt-hours per kilogram, whereas a lithium iron phosphate cell might exhibit a specific energy of approximately 100 watt-hours per kilogram, whereas a lead acid cell might only exhibit a specific energy of approximately 40 watt-hours per kilogram. This is to suggest that in order to deliver, let's say, 1 kilowatt-hour of energy, being 1,000 watt-hours of energy, it would take roughly 5.6 kilograms of lithium polymer cells, 10 kilograms of lithium iron phosphate cells, and a whopping 25 kilograms of lead acid cells to do so. If your concern is mobility, the clear choice is obviously the lithium polymer. If, however, your application is stationary and cost the primary concern, the clear choice is lead acid, because despite the comparatively poor specific energy, lead acid is known to be substantially cheaper than lithium polymer. In regards to volume, a lithium polymer cell might exhibit an energy density of approximately 440 watt-hours per liter, whereas a lithium iron phosphate cell might exhibit an energy density of approximately 220 watt-hours per liter, whereas a lead acid cell might exhibit an energy density of only approximately 85 watt-hours per liter. This is to again suggest that in order to deliver 1 kilowatt-hour of energy, being 1,000 watt-hours of energy, it would take roughly 2.3 liters of lithium polymer cells, 4.6 liters of lithium iron phosphate cells, and a whopping 11.8 liters of lead acid cells to do so. If your concern is space, the clear choice is obviously lithium polymer. If, however, you got a lot of space in your hands and cost the primary concern, the clear choice is lead acid, because despite the comparatively poor energy density, lead acid is known to be substantially cheaper than lithium polymer. Specific power is a tangentially related specification detailing how rapidly a battery can deliver power in relation to its mass. This is of primary concern for mobility applications or during periods of unusually large demand in which current must be rapidly withdrawn from a battery. A lithium polymer cell might exhibit a specific power rating of approximately 300 watts per kilogram, whereas a lithium iron phosphate cell might exhibit a specific power rating of approximately 240 watts per kilogram, whereas a lead acid cell might exhibit a specific power rating of approximately 180 watts per kilogram. In this case, a disparity exists, however, it isn't nearly as egregious as previously. If an application called for a peak power delivery of 2 kilowatts, it would take approximately 6.7 kilograms of lithium polymer cells, 8.3 kilograms of lithium iron phosphate, and 11.1 kilograms of lead acid cells to meet this peak demand. Again, power is different than energy. Power is the time rate production or expenditure of energy. Power is energy over time. Specific power ratings are a measure of how physically massive a battery might need to be to meet an intense but brief burst associated with inrush current characteristic to motor starters or applications with unusually excessive current draw. While we are on the topic of differences exhibited by different battery chemistries, consider the different safety and durability concerns. Lithium polymer cells with a nominal voltage of 3.7 volts have an annoying tendency to burst into uncontrollable flames when charged above 4.2 volts and/or punctured. It is for this reason that the charging and protection circuitry associated with lithium polymer cells needs to be reliable enough to prevent this occurrence from happening, and special handling precautions must be taken to prevent physical damage to the battery. A lead-acid battery, in contrast, is relatively more tolerant of overcharging. Notice I said relatively more tolerant. An excessively overcharged lead-acid battery can still be damaged due to swelling or loss of electrolyte, however, isn't normally known to burst into uncontrollable flames. Different chemistries are also associated with different self-discharge rates, which is essentially a slow leakage of the stored energy over time. A lithium iron phosphate battery might lose less than 10% of its stored capacity over a month, and a lead-acid battery only 5%. The internal chemistry of a battery also dictates its response to charge. A lithium iron phosphate battery might take only an hour to reach full capacity, whereas a lead acid battery might take 8. A lithium iron phosphate battery, however, essentially cannot be charged at sub-zero temperatures without a heater, whereas a lead acid battery can, although at a reduced rate. This do again suggest that no one battery and no one chemistry does it all. The lifespan of a battery is not only dependent upon its chemistry, but also a number of other factors, notably temperature, storage conditions, and principally how you treat it. A battery rode hard and put away wet will obviously not last as long as a battery that is regularly charged and only occasionally pushed to the limits. Depth of discharge is essentially the opposite of state of charge. If state of charge represents how much gas is left in the tank, depth of discharge represents how much gas you've removed from the tank. As mentioned previously, a full discharge causes strain, and each cycle permanently robs the battery of a small amount of capacity. Additionally, batteries that regularly experience a high depth of discharge and go long periods of time before being recharged will have a shorter lifespan than those that regularly experience a shallow depth of discharge and are immediately and properly recharged. Lifespan, depending on your perspective, might be defined as when a battery exhibits only 50% or 80% of the nominal capacity. A 230 amp-hour battery might be defined as reaching the end of its life when it exhibits only 115 amp-hours of capacity using the 50% standard, or 184 amp-hours of capacity if you use the more stringent 80% standard. A lead-acid battery that regularly experiences a 30% depth of discharge might last 1,200 charge-discharge cycles before it experiences a noticeable decrease in capacity. A lead-acid battery that regularly experiences a 50% depth of discharge might last only 500 charge and discharge cycles before it experiences a noticeable decrease in capacity. A lead-acid battery that is regularly pushed to the limits at 100% depth of discharge might only experience 200 charge-discharge cycles before it experiences a noticeable decrease in capacity. The wide range of cycles exhibited by the different chemistries include not only construction and manufacturer differences, but also different treatment patterns. A battery, quite like your imaginary girlfriend, will stick around a lot longer if you treat them well. This concludes the Introduction to Batteries lecture. Later lectures will go into greater detail about discharge characteristics, battery charging, and battery applications. In conclusion, we introduced the battery, an electrochemical energy storage device. We discussed general battery construction and the general chemical reaction for both the discharge and charge process. Additionally, we introduced and discussed the significance of the terms specific gravity, specific energy, specific power, C rating, nominal capacity, state of charge, depth of discharge, self-discharge, lifespan, and the unit amp hour. Finally, we differentiated between different types of battery chemistries, deep cycle and SLI batteries, FLA and VRLA batteries, and types of VRLA batteries like gel and AGM. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.